All right, everybody, welcome back to the start of another week. And believe it or not, we only have 6 more days of notes this week and next week. And then we will be done with the AP Calculus curriculum. So round of applause, pat yourself on the back, way to go, kudos to all of you. You guys have made it this far. Super proud of all of you. So let's get into chapter 7. And let's take off. So in this section, we're going to focus specifically on area. Now we have started area. We'll review what we already know, and then we're just going to take it to the next level. So what we already know about area. We first started with how to estimate area, and we looked at 3 approaches. We did RAM, we did trap, we did simp. And what that would do is find the area bounded on top by a curve and then on the bottom by the x-axis. So then we learned how to write that as an integral. And so this is going to be the upper boundary is the curve or the upper edge. And then the dx is telling us that we're bounded on the lower with respect to the x-axis. Okay, so it's between the curve and the x-axis. And then we learned the antiderivative, or Math 9, can evaluate that for us. So chapter 7, we're going to take that a little farther, and we're going to look at, well, what if we don't want the lower boundary to be the x-axis? What if we want the lower boundary to be a curve in and of itself? All right, so what if our upper boundary is still the f of x curve, but the lower boundary is some other function? Maybe partially above. Okay, here's a section where it's partially above the x-axis, maybe partially below. How do we determine the area that way? And it's really just a simple subtraction. The f of x comes first, and then you subtract the g of x function as your lower bound, and you do the subtraction algebraically, and then you proceed with your antiderivatives or your Math 9 if you can't do an antiderivative. So let's give this a try. So let's find the area of the region, not just between cosine x and the x-axis, but how about between cosine x and sine x from 0 to pi thirds? So I always like to have a visual so that I can understand what's going on here. So cosine x comes down, peaking at 1, coming down here. And we know that cosine is going to hit that at pi halves. All right, sine has a little bit of a different shape. So sine is going to be coming up through the origin and having its peak, and so we are intersecting, and we want to go from 0 to pi thirds. So a couple things we want to know about where these two things intersect. Let me back this up just a little bit. See if I can draw this a little bit more accurately so that I give us a good representation. Okay, let me aim for that spot right there. There we go. Okay, that's a little bit better. Okay, these two curves, sine and cosine, meet each other at pi fourths, right? We know that that is when sine and cosine are equal to each other. And so in this section, we want to find the area between them. And so remember that the upper is the cosine of x, and the lower right now is the sine of x. So how do we find that area of that red section? So the area is from 0 to pi fourths where they intersect each other. And the upper curve is the cosine of x minus the lower boundary, which is the sine of x. And then everything is moving from left to right along the x-axis. So we'll use basic antiderivatives to find the actual area. So the sine of x plus the cosine of x plus c, going from 0 to pi fourths. Sine of pi fourths plus the cosine of pi fourths minus the sine of 0 minus the cosine of 0. So we're going to look at the square root 2 over 2 plus another square root 2 over 2 minus 0 minus 1. So square root of 2 minus 1. All right, that is the area. Now, we are supposed to end at the directions, say, pi thirds. So there is a little bit more area up until pi thirds. So pi thirds is right here. So now we have some more area up till that point. And now the curves have changed order. The sine is now the upper curve, and the cosine is now the lower curve. So I'm just going to keep our area, and that green area now is going to go from pi fourths as it's beginning and ending at pi thirds, but this time it's the other way around. It's the sine of x as the upper curve minus the cosine of x as the lower, all with respect to the x-axis, moving left to right. So the antiderivative of sine is negative cosine, and then minus the sine of x plus c, as the bounds this time go from pi fourths to pi thirds. So the negative cosine of pi thirds first, minus the sine of pi thirds, plus the cosine of pi fourths, plus the sine of pi fourths. So all together, cosine of pi thirds is negative half, or minus half, minus rad 3 over 2, and then plus rad 2 over 2, plus another rad 2 over 2. So that's negative 1 minus rad 3 all over 2, plus rad 2. Okay, now the total amount of area are those two combined with each other, so that we've covered all the area together. So our total is rad 2 minus 1, and then I guess we could say minus a half minus rad 3 over 2 plus rad 2. So to simplify, we'll have 2 rad 2's, we'll have a minus rad 3 over 2, or minus 3 over 2, and a minus rad 3 over 2. Okay, and that's the exact area. You can confirm that each with a math 9. You could do a math 9 for the first set, and then a math 9 for the second set, and add those two together. Now let's look at, instead of trig, let's look at some parabola. So this time the bounds are not clearly given, so you're going to have to find the bounds yourself. Find the area of the region enclosed by the parabola x squared minus 1. All right, so visual, we know what that looks like. So we have our y-axis, our x-axis, and x squared minus 1 is going to come down. Okay, and y equals x plus 1. So here's negative 1, and then plus 1 up here. And we want the area enclosed by those two. So that'll be this area here. And so the upper is the equation x plus 1, and the lower is the parabola x squared minus 1. But we need to find these intersection points. Now you don't want to just eyeball it, you want to actually solve for the intersection points. So we need to know what these two intersection points are. So algebraically, we set the equations equal to each other. because if they're equal, then we know where they're intersecting. So as I'm going to subtract x, and I'm going to subtract 1. So then we'll factor to x minus 2 and x plus 1. So x is -1 and x is +2. So those are the values of the bounds. All right, so my integral, my area enclosed by these two, will be the integral from -1 to 2, and then x plus 1 comes first, and then subtract x squared. Make sure you change your sign when you subtract. So we're looking at -1 to 2. We've got -x squared plus x plus 2. And then relative to the x-axis. So we'll take our antiderivative, -1/3 x cubed plus 1/2 x squared plus 2x plus c, going from -1 to 2. So that's -1/3 of 8 plus 1/2 of 4 plus 4. And then minus, so we're gonna, so it'll be plus 1/3, but it's -1 cubed. And then minus 1/2 times -1 squared, and then minus 2 times -1. So -8/3 plus 2 plus 4 plus 1/3. Excuse me, nope, that'll be minus. Minus 1/2 plus 2. So I like to group my like terms together, which means fractions. So -8/3 and -1/3. So that's -3 plus 2 plus 4 is 6 plus another 2 minus 1/2. So what do we have with that all together? 8 minus 3 is 5, so 4.5. All right, so that is the overall area that's bounded and enclosed by the parabola on the lower end and the linear line on the upper part. Okay, this is going to be a calculator active, which means we need to set up our integral, but we're allowed to use Math 9 to help us, and we're also allowed to use our calculator to help us find our intersection spots. So e to the -x and cosine of x on 0 to pi. So remember that e to the -x comes down as a reflection, goes through the number 1. Once it crosses that x-axis, then it comes down to being asymptotic to the x-axis there. All right, and my graph for cosine dips down below the x-axis and then comes back up again for up to the boundary of 2 pi. All right, so we have this region here that we are trying to find the area of. And for that particular section, the cosine of x will be forming the upper boundary, while e to the -x is finding the lower boundary. Our job is to find this intersection spot here, and we'll use our graphing calculator, and we'll store that value. So set up your graph, make sure you're 0 to 2 pi, make sure you're in radian mode. Make sure, let's see, that your y-axis is fine to be like -2 to 2, should be fine. And we're going to do a second trace, and then we'll use the intersection to find what this value is. All right, so that value is 1.2926957. Now I'm going to save this and store this as alpha A on my calculator. So you want to quit from the graph that you're looking at, immediately hit from your home screen, hit store, and then alpha A, so that you've stored this value. now in somewhere in your calculator that it can refer back to it. So on your graph, you would always want to label for on the AP exam and for tests for me what letter that you've chosen to identify that as. And then we'll set up an integral. All right, the area is going to go from 0, and I can just say a. If I've labeled on my graph what the value of a is, then when I write my integral, all I need to do is put a. But I do need to specify that cosine x comes first, and then e to the negative x comes second. Now my second interval, so let's see here. We'll have this area here, and this time it's quite a large area, but this time the upper curve is now the e to the x, e to the negative x, excuse me, while the lower curve is the cosine of x. And we need to know what that intersection is here. And so we'll do another second trace, and we'll find the intersection value. And then we're going to store that probably as alpha b. All right, so this intersection value here is 4.7212928. But I'm going to assign that as alpha b on my calculator. So again, do a quit, do an immediate store, and save that as alpha b. Then when you come back to your integral, we're going to put plus, and we're going to say a to b. And then e to the negative x is the upper, and then minus the cosine of x as the lower. For the final region of area, the boundaries, the upper and the lower values of the functions, they switch back, and then we're going to stop at 2 pi. So my final integral will start at b and end at 2 pi, and then we're back to normal again with cosine of x minus e to the negative x dx. Now your calculator can totally handle all of that. You can type all of that in one line. If you want to do them all individually, you can, but you don't have to. You can do a Math 9 0 to a, remember, because you've stored alpha a in there, and then you'll have your e to the negative x, cosine, excuse me, first, and then minus e to the negative x. And then you could just add on that same, as long as you're using parentheses correctly, you can just do an add right after, and then do a second Math 9, and then a third Math 9. And so all of that together, 1.465140827. So we can round to the nearest thousandth there, so 1.465. So Math 9 is beautiful, really helpful. So just be aware when you can and can't use your calculator. If you are grayed out, then you will need to find the bounds by hand using algebraic methods, and you'll need to find the area by hand, again, using algebraic and antiderivative methods. If you've got your calculator, then you can store those intersection points and use Math 9 to find the area between these two curves. All right, so I will see you guys tomorrow on Tuesday as you have worked your way and gotten, some practice with some of this area stuff. All right, see you then.